All right, so diving right in. We're tackling quantum computing today. You've given us a really interesting mix here. Articles, research, everything from the basics to some pretty mind-bending potential applications.
Yeah, it seems like you're looking for a solid understanding of how it all works, what sets it apart from our everyday computers, and the impact it could have on different industries.
Exactly. Think of this as your quantum computing cheat sheet. We're going to break it all down. Hit the highlights from your sources and explore what this technology could really mean for the future. And trust me, some of it is straight out of science fiction. Like one article mentioned, simulating molecules. Imagine designing a drug specifically for your DNA. That's the kind of wild stuff we're talking about here.
Yeah, that's just one possibility. To really understand the scope of what quantum computing can do, I think we first need to understand how different it is from classical computing.
Okay, let's start there. What's the core difference?
It all comes down to how they process information. Classical computers, like the one you're using right now, rely on bits. They can be either a 0 or a 1, but not both at the same time. Quantum computers, however, use qubits.
Now, these qubits are where things get really interesting, right?
Exactly. Qubits can be a 0, a 1, or both simultaneously. This is called superposition. It's kind of like, imagine you're flipping a coin. A classical bit is like that coin landing on either heads or tails. A qubit is like the coin spinning in the air. Until you stop it, it's both heads and tails at the same time.
So it's not just a matter of more powerful hardware, it's a completely different way of thinking about information.
Precisely. Qubits allow quantum computers to explore many possibilities at once, giving them the potential to solve problems that would take classical computers millions of years.
One of the articles you sent mentioned something called quantum advantage.
Hmm.
What exactly does that mean?
Quantum advantage is the point where a quantum computer can solve a practical problem significantly faster or more efficiently than a classical computer. Think about optimizing delivery routes. For a massive logistics company, a classical computer would have to crunch through each possible route one by one. A quantum computer, thanks to superposition, could explore all possible routes simultaneously. That's a huge time saver, potentially leading to faster deliveries and lower fuel costs.
Okay, that makes sense. But this superposition thing, it seems like something out of Star Trek. Where does this quantum weirdness come from?
That's where quantum mechanics comes in. It's a branch of physics that studies the behavior of matter at the atomic and subatomic levels, and the rules are very different down there.
Different how?
Well, one of the key principles is wave-particle duality. It's the idea that particles can act like waves, and waves can act like particles.
So it's like a tiny piece of matter could be in two places at once.
In a way, yes, it's this wave-like behavior that allows qubits to exist in a superposition of states.
All right, my head's spinning a bit, but I think I'm starting to get it. So we've got superposition. But I know there's another quantum phenomenon that's important here. Entanglement.
You're right. Entanglement is where things get really spooky. Imagine you have two entangled qubits. When you measure the state of one, you instantly know the state of the other, no matter how far apart they are.
So it's like they're connected by an invisible thread.
Exactly. And this seemingly impossible connection plays a huge role in quantum computing's power. In fact, it's one of the things that makes quantum communication and cryptography theoretically possible.
That's incredible. So we've got these qubits that leverage superposition and entanglement. But what can we actually do with them?
Yeah.
Where does this quantum power translate to real-world results?
The possibilities are vast,
Yeah.
and we're really just starting to explore them. One of the most promising areas is drug discovery. Imagine being able to simulate how a drug interacts with a specific protein at the atomic level, potentially leading to treatments for diseases like Alzheimer's or Parkinson's that have stumped researchers for decades.
Wow, that's huge. No more trial and error with medications. We'd be designing drugs with pinpoint accuracy.
That's the idea, and that's just one example. Quantum computers could also revolutionize material science.
Listening?
Right now, developing new materials is often a slow and expensive process. With quantum computers, we could simulate the properties of materials before we even create them in the lab. Imagine designing a new super strong, lightweight material for, say, building spacecraft or more efficient solar panels.
Okay, so healthcare, material science, what else?
Let's not forget finance. One of the articles you provided mentioned how quantum computers could potentially revolutionize financial modeling. They could analyze massive data sets to identify patterns and trends that would be invisible to classical computers, leading to more accurate risk assessments, better investment strategies, and maybe even new ways to prevent fraud.
So we're talking about potentially impacting huge industries. But before we get too carried away with all these amazing applications, let's dive deeper into the heart of a quantum computer. The qubit.
That's a good point. Understanding how qubits are actually built is key to grasping the challenges and the possibilities of this whole field.
All right, let's do it.
As we've said, a classical bit can be either 0 or 1. A qubit, however, leverages superposition to exist in a combination of both states. It's like having a dial that can point to 0, 1, or anywhere in between.
So it's not just about the two extremes. It's about exploring the entire spectrum of possibilities.
Exactly. And this ability to hold multiple values simultaneously is what gives quantum computers their immense processing power. They can explore many computational paths at once, unlike a classical computer, which has to go through each path one by one.
That's mind-blowing. So these qubits sound incredibly powerful. But I know it's not all smooth sailing. Aren't there different types of qubits? And doesn't that create challenges in building these computers?
You're right. There are several approaches to building qubits, each with its own advantages and disadvantages. Some of the leading technologies include superconducting qubits, trapped ions, and photonic qubits. For this deep dive, let's focus on superconducting qubits, as they're one of the most mature technologies right now.
All right, superconducting qubits it is. Let's break them down.
Superconducting qubits are tiny electrical circuits that operate at extremely low temperatures, just a few degrees above absolute zero.
We're talking colder than interstellar space here.
Much colder. At these temperatures, the materials in the circuit exhibit superconductivity, meaning electricity flows through them with zero resistance.
Okay, so the electrons are basically gliding through without any friction.
Yeah.
But how do these circuits represent qubits?
The qubit is encoded in the energy levels of the circuit. Think of it like a tiny swing that can swing back and forth. The lowest energy level represents the 0 state. A higher energy level represents the 1 state. However, unlike a normal swing, a superconducting qubit can exist in a superposition of both energy levels at the same time.
So it's swinging both ways at once. That's wild.
That's the power of quantum mechanics. And by controlling the energy levels of the circuit, we can manipulate the state of the qubit and perform computations.
So these superconducting qubits are like the individual building blocks of a quantum computer.
Exactly. And by connecting multiple qubits and controlling their interactions, particularly taking advantage of entanglement, we can build more complex quantum circuits capable of tackling really complex problems.
It all sounds incredibly complex,
Yeah.
but also incredibly promising.
It definitely is both. Building and operating a quantum computer is a feat of engineering and physics, unlike anything we've seen before. And while the challenges are significant, the potential rewards are even greater.
So we've got a handle on the basics of quantum computing, the idea of qubits and superposition, and even how superconducting qubits work. But what about those real-world applications? I'm ready to hear more about how this could change the world.
Let's get into it. Welcome back to our deep dive into quantum computing.
All right, let's pick up where we left off. We've covered the basics of quantum computing and how it differs from classical computing. We even delved into the intricate world of qubits, specifically superconducting qubits.
We explored how these qubits leverage the bizarre but fascinating principles of quantum mechanics, like superposition and entanglement, to carry out computations in a completely different way.
We even touched on some of the mind-blowing potential applications, like revolutionizing drug discovery and creating entirely new materials.
But as with any emerging technology, there's a flip side to this quantum coin. We need to talk about the challenges, the hurdles that researchers are facing in bringing quantum computing to its full potential.
That's a crucial point. It's easy to get caught up in all the excitement, but it's important to understand the complexities and limitations as well. So let's dive into those. What are some of the biggest obstacles standing in the way of practical quantum computing?
One of the most significant challenges lies in maintaining qubit coherence. Remember how we talked about qubits being supersensitive? Even the slightest disturbance, like a change in temperature or stray electromagnetic fields, can cause them to lose their quantum state.
Right, those qubit divas needing their perfect condition.
Exactly. And when a qubit loses its coherence, it's like dropping that spinning coin we talked about earlier. The delicate balance collapses, and you're left with just a regular bit. This loss of coherence leads to errors in calculations, which can completely derail the entire quantum computation.
So it's like trying to build a house of cards on a shaky table. One wrong move and the whole thing falls apart.
That's a good analogy. And the longer a computation runs, the more likely it is that these errors will accumulate, making it incredibly difficult to perform complex calculations reliably.
So how are scientists tackling this coherence problem? Are there ways to make these qubits more robust, less susceptible to these environmental disturbances?
Researchers are working on multiple fronts. One approach involves designing and engineering more robust qubits from the ground up. Qubits that are inherently less sensitive to their surroundings. Think of it as building a sturdier house of cards with thicker, heavier cards that can withstand more shaking.
Okay, so making the qubits themselves more resilient. What else?
Another strategy involves developing sophisticated error correction techniques. It's like having a system in place to constantly monitor the house of cards and gently nudge any cards that start to wobble back into place.
That's a cool way to think about it. So it's a combination of building better qubits
Mhm.
and creating these quantum safety nets to catch and correct errors as they occur.
Precisely. Both approaches are essential for achieving the goal of fault-tolerant quantum computing, where errors are minimized and complex computations can be performed reliably.
Now, aside from the delicate nature of qubits, there's also the immense challenge of actually building and scaling these quantum computers. We're not talking about just adding a few more transistors to a chip here, right?
You're absolutely right. Constructing a quantum computer is an extraordinary feat of engineering and physics. It requires manipulating matter at the atomic level, maintaining incredibly precise control over temperatures and electromagnetic fields, and ensuring that all the delicate components work together seamlessly. It's more akin to building a spaceship than assembling a laptop.
It sounds almost impossible. So how close are we to seeing practical, large-scale quantum computers?
We're still in the early stages, but the progress is accelerating rapidly. Companies like Google, IBM, and Microsoft are investing heavily in this field, and we're seeing incredible breakthroughs in qubit design, coherence times, and error correction techniques.
So there's a real sense of momentum, a global effort to crack the code of quantum computing.
Absolutely. And while it's difficult to predict exactly when we'll have powerful, fault-tolerant quantum computers readily available, the trajectory suggests that we're heading in that direction faster than many people anticipated.
That's exciting to hear. But before we get too caught up in the technical details, let's zoom out a bit and talk about the bigger picture. As we move closer to practical quantum computing, what are some of the ethical and societal implications we need to consider?
That's a crucial point. Powerful technologies often come with profound responsibilities, and quantum computing is no exception. One of the most pressing concerns is the potential impact on cybersecurity.
Right. We touched on that earlier. Quantum computers could potentially shatter the encryption methods that underpin our digital world.
Exactly. Imagine a world where all our online transactions, sensitive data, and national secrets are suddenly vulnerable to attack. It's a scenario that cybersecurity experts are taking very seriously.
So it's like a race against time. While we're developing these incredibly powerful quantum computers, we also need to be developing equally powerful safeguards to protect our digital infrastructure.
That's precisely the challenge. Fortunately, alongside the advancements in quantum computing, there's a parallel effort to develop what's called quantum-resistant cryptography. It's a new breed of encryption algorithms, specifically designed to withstand attacks from even the most powerful quantum computers.
So it's a bit of a cryptographic arms race. On one side, we have quantum computers that could potentially break existing codes. And on the other side, we have cryptographers working tirelessly to create new, unbreakable codes.
It's a fascinating dynamic, and one that highlights the importance of collaboration and foresight in navigating the complex landscape of emerging technologies.
Now, beyond cybersecurity, are there other ethical considerations we should be thinking about?
Absolutely. One concern is the potential for misuse. Imagine quantum computers being used to develop autonomous weapons systems or to enhance surveillance capabilities to unprecedented levels. These are not scenarios we want to see unfold.
Those are some unsettling possibilities. It seems like with any technology this powerful, there's always the risk of it being used for harmful purposes.
That's why it's so important to have these conversations now, to engage in open and honest discussions about the ethical implications of quantum computing, and to establish guidelines for its responsible development and use. We need to ensure that this technology serves humanity, not the other way around.
I completely agree. And as we think about the broader societal impact, there's also the question of job displacement. If quantum computers can perform tasks that currently require human expertise, what happens to those jobs and the people who hold them?
It's a valid concern. Automation has always been a double-edged sword, bringing efficiency and progress, but also potentially displacing workers. And with quantum computing, the scale of potential automation could be significant. It's not just about replacing manual labor, but also potentially impacting jobs that require complex decision-making. data analysis, and even creative thinking.
So as we move towards a quantum-powered future, we need to be proactive in addressing these workforce challenges. It's not just about developing the technology,
No.
but also about preparing people for the changing landscape of work.
Absolutely. We need to invest in education and training programs that equip people with the skills and knowledge to thrive in a world where quantum computers are increasingly prevalent, and we need to create opportunities for people to transition into new roles that leverage their human capabilities, those skills that are unlikely to be easily automated, such as creativity, empathy, and critical thinking.
So in a way, quantum computing is forcing us to confront some fundamental questions about the nature of work, the value of human skills, and the kind of future we want to create.
It is. And it's a reminder that technological advancements, while exciting and full of potential, should never be viewed in isolation. We need to consider the broader societal, ethical, and human dimensions as we navigate the uncharted territory of quantum computing.
Well said. We've explored the potential of quantum computing to revolutionize various industries, from medicine to materials science to finance. We've also delved into the complex challenges, the delicate dance of qubits, and the need for robust error correction. And we've touched on the ethical considerations, the potential risks, as well as the profound responsibilities that come with wielding such a powerful technology.
We've covered a lot of ground, but our journey isn't over yet. There's still one more piece of the puzzle to explore: the future of quantum computing. What breakthroughs and advancements can we expect to see in the years to come? And how will this technology ultimately shape our world?
All right, we're back for the final part of our quantum deep dive. So far, we've explored the fundamental ideas behind quantum computing, tackled the complexities of qubits, and even grappled with the ethical considerations.
Yeah, we've examined how this technology could potentially reshape industries, from healthcare to finance, and discussed the ongoing efforts to overcome the hurdles of qubit fragility and scalability.
Right, but now let's shift our focus to the future. What's on the horizon for quantum computing? What breakthroughs are scientists working towards, and what kind of world could this technology create?
The future of quantum computing is a landscape brimming with possibilities. It's a field that's constantly evolving, with researchers pushing the boundaries of what we thought was possible. One area where we can anticipate significant progress is in qubit technology itself.
So those finicky qubits are getting an upgrade.
Precisely. Scientists are relentlessly pursuing ways to develop qubits that are more stable, less prone to those coherence-breaking errors, and easier to scale up. Imagine a future where qubits are no longer those delicate divas, but robust workhorses capable of handling complex computations without breaking a sweat.
Now that would be a game changer. So what are some of the promising avenues researchers are exploring in this quest for better qubits?
There's a whole quantum zoo of different approaches. We've talked about superconducting qubits, which are currently leading the pack. But there are also trapped ion qubits, where individual atoms are suspended using electromagnetic fields, and photonic qubits, which use particles of light to encode quantum information. Each approach has its own set of advantages and challenges.
It's like a quantum race, with different teams competing to develop the most powerful and reliable qubit technology.
Exactly. And it's a race where everyone benefits from the collective progress. Ultimately, the goal is to create qubits that can maintain their quantum states for extended periods, enabling us to perform longer and more intricate computations.
So it's about building qubits that are not just individually stable, but also work well together as a team.
Precisely. And this brings us to another crucial aspect: scalability. Right now, the most advanced quantum computers have hundreds of qubits. But to truly unlock the potential of this technology, we need to reach thousands, even millions of qubits working in harmony.
That sounds like a monumental task.
It is. Scaling up a quantum computer isn't simply a matter of adding more qubits. It's about ensuring that they all remain interconnected and can communicate effectively, all while maintaining the delicate balance of their quantum states. It's like trying to choreograph a ballet with millions of dancers, each performing intricate movements while remaining perfectly synchronized.
Okay, that analogy definitely paints a vivid picture of the complexity involved.
But despite the challenges, the progress in scalability has been remarkable. And with the combined efforts of research institutions, tech giants, and government agencies, we're steadily marching towards the era of large-scale, fault-tolerant quantum computers.
That's encouraging to hear. Now let's move beyond the hardware for a moment. What about the software side of things? What advancements can we expect to see in quantum algorithms, the instructions that tell these quantum computers what to do?
The development of quantum algorithms is just as crucial as building the hardware. after all. Even the most powerful quantum computer is useless without the right instructions to guide it. Researchers are constantly developing new algorithms that can harness the unique capabilities of quantum computers to tackle real-world
So
problems.
it's like having a powerful engine, but needing a skilled driver to steer it in the right direction.
Exactly. And there are certain areas where quantum algorithms are expected to outperform classical algorithms by a wide margin. One example is quantum simulation, where we can use quantum computers to model complex molecules or materials, potentially revolutionizing fields like drug discovery and materials science.
We've talked about those possibilities before, and they're truly mind-boggling.
Another promising area is quantum optimization, where we can use quantum algorithms to find the best solution among a vast number of possibilities. This has applications in fields like logistics, finance, and even artificial intelligence.
So quantum computers could help us solve some of the most complex optimization problems that are currently intractable for classical computers.
Precisely. And this leads us to one of the most exciting frontiers in quantum computing, development of quantum machine learning algorithms.
Okay, machine learning is already transforming so many industries. How could quantum computing take it to the next level?
Imagine machine learning algorithms that can process information exponentially faster, identify patterns that are hidden from classical algorithms,
Hmm.
and make predictions with unprecedented accuracy. That's the potential power of quantum machine learning. It could revolutionize fields like medical diagnosis, drug development, financial modeling, and even the search for extraterrestrial life.
Wow, those are some pretty big claims. So you're saying that quantum computing can not only solve some of our most pressing challenges, but also open up entirely new frontiers of knowledge and discovery.
That's the beauty of this technology. It's not just about doing things faster or more efficiently. It's about expanding the realm of what's possible. It's about pushing the boundaries of human knowledge and understanding.
As we wrap up this quantum deep dive, I'm struck by a sense of both awe and excitement. We've explored the strange and counterintuitive world of quantum mechanics, witnessed the incredible ingenuity of scientists and engineers, and glimpsed a future where quantum computers could reshape our world in profound ways.
Yeah. It's been an incredible journey, and as we stand on the cusp of this quantum revolution, it's important to remember that the future is not predetermined. The choices we make today, the investments we prioritize, the ethical guidelines we establish, all of these factors will shape the trajectory of quantum computing and its impact on humanity.
So while we marvel at the potential of this technology, we also need to approach it with a sense of responsibility and a commitment to using it for good.
Absolutely. Quantum computing is a powerful tool, and like any tool, it can be used for both constructive and destructive purposes. It's up to us as a society to ensure that this technology is used to advance human knowledge, solve global challenges, and create a more just and equitable world.
Well said. And as we conclude this deep dive, I want to leave our listeners with a final thought. Stay curious. The world of quantum computing is constantly evolving, with new breakthroughs and discoveries emerging all the time. Keep exploring, keep learning, and keep asking questions. Who knows what incredible possibilities await us in this uncharted quantum frontier?
It's a journey worth taking.